Ciao Nicola.
Ciao, Gustavino.
No,
Ciao a tutti.
Ciao Nick.
Ciao. I cannot start the video, so hi.
Live. Live on YouTube.
Ciao Nicola.
Ciao.
Ehi Nicola, ciao ciao.
Buongiorno a tutti.
buongiorno.
Salve.
Buongiorno.
So we wait a couple of minutes. We see that there are many people that are connecting now. So just to wait a little bit. Okay, I think that we could start now. So first of all, welcome to everybody. It's a great pleasure for me to introduce this presentation of Nicola Rossi concerning the new measurement of Borexino detector. I think that is a very important result, has a very important impact on our understanding on stellar evolution and stellar cycles. And I think that I'm very happy to see that this result was at the end obtained after a very strong effort that was spent by the Borexino collaboration in order to achieve the right condition for this measurement. So I would like, first of all, to congratulate with Nicola first, but with all the collaboration, Borexino collaboration for this very impressive result and this very important achievement that is, in my opinion, a very important step in our, let me say, in our understanding of the solar, complete solar evolution and solar characterization. So I don't think that it's useful to spend more time in this direction. I think that Nicola have many things to present to us and to discuss, and so I will leave to Nicola the space. I would like to start with the presentation of Nicola in order to go ahead in this direction. At the end, we will have some discussion, I hope, and we will ask Nicola some specific part. Okay, please, Nicola.
Okay, hi everybody. Thank you for the introduction, Ezio. Okay, let me start. First of all, I would like to start with a kind of joke because I put first in front of the title, because in the original paper published last November 26, it's written only experimental evidence of neutrino production in the CNO fusion in the cycle in the sun, and it's missing first because, you know, the policy of nature sometimes it's not that easy to do strong statement, and if you put first, you should add also to our knowledge. So that's the reason why we decided to remove this, but for sure we know that is the first experimental evidence of the CNO neutrinos. The story I want to tell you about, it's very old and dates back probably even before the 19th century, but I should mention probably the ancient Greece, in which they probably they were the first scientists that were thinking seriously about the nature of the sun, the planets, and everything that is surrounding us. And I want to mention, for example, Aristarchus of Samo, who made the first hypothesis regarded that the sun is the center of the universe, but not only. Before Eratosthenes, he measured the distance from the Earth and the Sun, and also the sides, the diameter of the Sun, the Moon, and the relative distance. It is really important to mention this important starting of the science in the ancient Greek. And also, I want to mention Archimedes, who first understood the fact that a body that is self-attracting at its liquid should have a spherical shape. Not only, they grasped also the basic idea that the nature of the gravity is polycentric, because if the planets are spherical, and we know that the Earth is spherical because probably it was liquid in the past, they made also some kind of statement. There should be this attraction should be in different centers, and probably they anticipated with this concept also the gravitation, the theory of the gravity, then of course proposed by Newton later. But let's go to the modern science period, and it's the 19th century. After the establishment, after the completion of the thermodynamics, scientists were asking what is the energy source of the sun, because they could not believe, as philosophers in the past, that sun is shining because it's kind of something infinite that is always emitting light. knowing the thermodynamics, the laws of the thermodynamics, that you should have a source. You should try to understand what is the source of the energy. At that time, for example, it was known the source from the chemical reaction, like the burning of the coal that was the power for the industrial revolution. And if you, for example, make the hypothesis that the sun is made of coal and it's simply burning, the sun should last for 3,000 years, that it's really short, not even comparable with the records for the story, the history of the mankind. And then they were also thinking about some other possible origin. And the other origin could be the gravity, because you can imagine that at the beginning you have a big cloud that is collapsing, and this gravitational energy is transformed, is converted into kinetic energy, and gives the power, the high temperature to the sun to shine. But also in this case, the sun should cool down. And people like William Thomson, also known as Love Kelvin, but also before Helmholtz and other scientists, were making some rough estimation, and they believed that if this is the true mechanism that gives the power to the sun should cannot be older than 20 million years. Considering also, for example, meteorites falling on the sun and increasing the energy content on the sun. And for sure, there was at that time a controversy with the age, for example, of the Earth coming from the geology. One of the first estimate of the age of the Earth, for example, was done by Charles Darwin, because he was interested in a very long time period in order to have time for the evolution to produce all the species existing on the Earth. That we know now it's a very long time, because it's billions of years. And he made a rough estimation looking at the geology. For example, you can understand that the age of the Earth should be really, how to say, long, because, for example, imagine that the water that is digging a canyon, so you require a lot of time for producing what we observe from the mountain and etc. And so he made estimation of like 300 million years. That was, of course, not in contradiction with the number presented by William Thomson. But at that time, they didn't know that there was a new physics, something that should be discovered for understanding the real mechanisms. And that's the reason why the discussion was almost stopped. But it's also interesting because Darwin himself wrote, for example, that for sure there is something that we don't understand from the chemistry. Maybe in the intimate nature of the atoms, there should be some kind of energy that when we meet the special condition with high temperature as inside the sun, this energy should come out and produce all this energy sufficient for making the sun shine for a very, very, very long time. And it happened at the end of the 19th century, it was discovered the radioactivity. And so there was some new hint about the intimate nature of the atoms and the nuclei in particular. And not only in that period, there was also Einstein with the special relativity, so the possibility of converting mass into energy through the E equal mc² formula. And they started thinking that probably there is some other mechanism happening in the nuclei that are producing this big amount of energy. And it was also interesting because in 1920, Aston published the first high precision measurement of the light nuclei. And for example, they observed that a helium atom, it's not exactly 4 times bigger as an hydrogen atoms, but there is a small mass defect that could be, maybe can explain this extra energy inside the sun. And at that time, they also started to study the chemical composition on the sun. At the beginning, for example, they made also the hypothesis that the sun is made of heavy elements like radium that can decay and warm up the sun. And so, as the physics of the atoms was understood, in the end, around 1938, independently, von Weizsäcker and Bethe proposed independently mechanisms for the conversion of the hydrogen into helium that now we know as the PP chain and CNO cycle. And this is the subject, of course, of this presentation. So we know now the mechanism, what makes the sun shining for such a long time, that it's very big. We know that should be like 5 billions of years, that it's also comparable with the measurement of the age of the Earth that was also started in that period that when the radioactivity and the uranium dating was discovered. And then after the Second World War, we have, for example, big scientists as John Bacall, who made the basis of what we call now the solar standard model, that is also the basics for the astrophysics in general. So what do we know now about the mechanism of the hydrogen burning in the sun? There are two mechanisms, and we know that in the sun, given the temperature, and that it's related, of course, to the mass of the sun, 90% of the energy is produced by the PP chain that is initiated by essentially two processes in which the PP process is dominant, that is the conversion of PP into deuterium atom. And then there is this secondary process that is called PEP or PEP, in which it's a tri-body radiation that produce, even in this case, the deuterium atom, and start the process that make the fusion of 4 atoms of hydrogen into helium. And then we know that given the condition, the physical condition in the sun, and the abundance of the elements heavier than helium, there should be also a second cycle that should contribute like 1% to the total energy, that is called CNO, in which there is a closed loop starting from the carbon-12 that works as a catalyst that makes exactly the same as the PP chain. In the end, passing through nitrogen and oxygen, you get another carbon-12 plus a helium atom. So the same mechanism, but catalyzed by the carbon-12 atom. And what is the competition between the two processes? Given the temperature of the sun, that is 15 something million Kelvin degree, the mechanism, the energy production is basically dominated by the PP chain, but for stars heavier than 1.3 the solar masses, this is the dominant mechanisms. And because it becomes more efficient, and it's the way to convert efficiently hydrogen into helium, produce a lot of energy with a lot of radiation pressure to compensate the gravitational collapse, and so makes bigger stars live as well as for the sun, but with a different thermodynamic condition. But what is interesting for us is that associated with this reaction, with this processing, there are emission of neutrino. I don't need to explain what is a neutrino. I want just to remind you that neutrino are really special particles because they are interesting for the particle physics themselves, because they can help us to understand the logic of the fundamental interaction and the relation between the particles, but also are important for the astrophysics, because we know that neutrino is weakly interacting, so can pass through the outer surface of the sun from the core where it is produced without interacting, and so it can give the information of the reaction happening in the core of the sun. And neutrino is also famous in the solar physics because it's related to the solar neutrino problem, missing the famous story of the missing neutrino. And so whatever, it was fundamental for understanding this strange property of the neutrino, that is the neutrino oscillation. And we studied all this kind of neutrinos with different experiments, in particular with Borexino, as I will tell you later. And it's very easy for the neutrinos coming from the PP because they are abundant, but it's not easy for the CNO neutrinos because since the CNO cycle in the sun is contributing only to 1%, of course the flux is low as compared with the neutrinos coming from the PP. But these neutrinos are really important because the CNO neutrino, I mean, because not only they tell us about the existence of this fundamental process that we can observe from our star, and then we can extrapolate for heavier stars, and so we can understand the basic mechanisms of hydrogen conversion in the universe, and so the fundamental understanding of the astrophysics, but also because it's fundamental for understanding and solving what is called in the solar modeling, what is called the solar metallicity problem. That means the controversy between the estimation of the quantity of elements greater than helium that comes from independently from the measurement of the surface of the sun and from it is deduced from the helioseismology that basically concern the sound speed and all the properties inside the sun. So these two measurements do not agree each other, and this problem it's still unsolved, and it's referred as a solar abundance problem. And so CNO, the precise measurement of the CNO neutrino are crucial for the solution of this puzzle. Borexino played an important role in understanding and measuring basically all the fluxes coming from the PP chain. Just a short story of the experiment. The experiment started with a paper from Raju in 1988, and the first the idea of the experiment started in 1990, and here there was a key role, for example, for the Italian professor Giampaolo Bellini, who is the third from the left in the picture, and also from Frank Calaprice, who is the second. From Princeton University. Both played an important role for the construction and of the experiment, and also all the long saga of the experiment that started exactly 30 years ago. At the beginning, it was understood that for having a real-time detector for measuring the low sub-MeV neutrinos, it was required the radio purity at a very regular level. It was clear that the contribution from uranium and thorium chain should be less than 10 to 16 gram per gram, and the carbon-14 should be lower than 10 to minus 18. Of course, it was not possible to measure such a low radio purity with standard techniques like mass spectrometer available. And so there was it was built a prototype that was called the CTF, Counting Test Facility, in which it was proven that this record level of radio purity of the material is reachable. The experiment was approved in 1996-97, and the real data taking, so the final construction of the detector, started in May 2007, so 13 years ago. This was possible because Borexino not only we will see not only measured the beryllium-7 neutrino, but also was sensitive to basically all the neutrinos coming from the PP chain, thanks to its radio purity. Radio purity for the choice of the material in which the of which the detector is made of, and the unprecedented techniques used for the purification of the liquid scintillator. I will speak about it later. This is basically the result of the best of the Borexino result before our publication this year about the CNO. For Borexino, made the first real-time spectroscopic measurement of the PP neutrinos with 10%, about 10% precision. Borexino made the first and then the precision measurement of the beryllium-7 at 3% level. Borexino made the first evidence and then finally the discovery at 5 sigma, at more than 5 sigma of the PP neutrino, made the first low threshold boronate detection at 3 MeV. And also this result was updated later in 2018, and the best limit of this secondary very suppressed reaction present in the CNO cycle. And then up until this present work, for the CNO, we had the strong limit that was 8 CPD per 100 ton. We should get used to this unit, that it's the human readable unit that we use for evaluating the radioactivity and the interaction rate of our event. And okay. And what are the implications of the Borexino? On the left, you can see the electron neutrino survival probability made only with Borexino. And this is quite important because in this way you can factor out all the systematics that can come from the different experimental techniques, because we have the same techniques and you look at the survival probability for different energy, even if the precision it's not very high. I mean, for allowing no standard interaction, whatever you need, but we are probing basically the standard large mixing angle solution for the neutrino oscillation in the MSW matter enhanced scenario, and we are compatible pretty well with this scenario. And for example, the absence of the MSW oscillation is ruled out at more than 98% using our result. And we had also in 2018 some hint about the metallicity problem that I told you, between which one is the best between low and high metallicity. And using Borexino only data, all the fluxes from the PP chain that are a bit sensible to the metallicity, not as for the CNO, but still they are. And we can disfavor the low metallicity at 1.8 sigma. And so this was the best knowledge before this publication. Okay, let me speak about Borexino experiment, because I see that there are people that probably didn't visit our laboratory. Borexino is located in the Old Sea of Grand Sasso National Laboratory. Here we have good shielding against the muons. The overburden is about 4,000 meters of water equivalent, just for being practical. The muon flux underground, it's something like order of 1 per meter square per hour. That it's extremely low, but could be anyway a problem for big detector as Borexino, which has a very big surface. This is the scheme of the detector, and was really crucial for the sub-MeV solar neutrino detection. You see, it's Borexino. It's a matryoshka-like structure with increasing radio purity. Basically, it's a big sphere containing something like 1,300 cubic meter of pseudocumin with a hydrocarbon. And this sphere is divided inside by two nylon balloon, extremely radio pure and thin, and only inside the innermost sphere, that is called inner vessel, there is the PPO added to the pseudo-Q-mean, and this works as a scintillator. On the sphere, we have like 2000 photomultipliers that are collecting the scintillation light, and all the sphere is immersed inside a water Cherenkov detectors, a water Cherenkov detector of about 2000 cubic meter of water, with instrumented with 200 photomultipliers on the floor and on the outer surface of the sphere. These are pictures of the Borexino inside, of course, during the construction, before the filling. You can see the sphere from outside, then the view of all the photomultipliers inside. Photomultipliers are 8 inches, and the total optical coverage is about 34%. And here you can see the balloons supported by these nylon ropes that gives the shape and hold the balloon themselves. This is Borexino today. Sometimes we can turn on the light, even if this is not a really good procedure, because our electronics and photomultipliers are very old, and when you turn on the light, you can damage them. But sometimes we need to check inside if everything is properly working, and we see that clearly. The balloon is still there in the same position, and it's not really changed. We have two different methods for evaluating the position of the vessel. One is from the camera when we get the picture, and the other that we can do week by week is done using the contaminants. So there is an algorithm that it's looking at the vent, the contamination, the vessel surface, and so we can reconstruct with a precision of few centimeters the position of the inner vessel. And this is really important because we defined what is called the dynamic fiducial volume. So the possibility also for a given types of analysis to change accordingly, follow the small evolution a few centimeters of the inner balloon. And this other picture, it's outside, how Borexino looks like in the whole sea. And we will see why the Borexino is wrapped with this kind of blanket around, because this was really crucial for the measurement of the CNO. Okay, these are the three ages of Borexino. Borexino was young at the beginning, middle age, and now it's old. And we called this phase 1, phase 2, and phase 3. In the first phase, we had the first experimental evidence of the barium-7. Then there was a deep calibration campaign that was fundamental for tuning the parameter for the modeling of the response and the resolution of the detector. Then we had this other important operation that was crucial for the precise measurement of the phase 2 and also for the measurement of the CNO. This was really crucial and was the water extraction. I will speak about this later. It was fundamental for reducing the background and bring the detector to an unprecedented level of radio purity. Then there was an important operation that started in phase 2 and it's still lasting for all phase 3, still active even today. That is the thermal insulation program that was crucial for the CNO. We understood this at the beginning in 2013 when we started doing the first feasibility study for the CNO. And the plan was actually scheduled in 2014, and then we started doing this program in mid-2015. Okay, and the last is the phase 3, and this is basically the data taking period that was used for the present publication, for the present result. What is the detection principle of Borexino? Basically, we are detecting the elastic scattering of a neutrino of electrons. electrons are releasing energy, so they are producing scintillation light collected by the photomultipliers. Borexino is sensitive to all types of neutrino, of course, with the neutral current for mu and tau, and neutral charge current for the electron neutrino. Of course, we account for this kind of weighted average, if you like, for the cross-section of the two processes, and we consider it when we, for example, estimate the survival probability as a function of the energy that I showed you before. The calibration campaign was really important because it was useful for we basically deployed inside the detector standard gamma sources and other types of gamma, and this was fundamental for tuning the energy calibration and the position reconstruction, because using the time of flight of the photons collected by the photomultipliers, we can reconstruct the position of the event with an uncertainty of about 10 centimeter at 1 MeV for an electron at 1 MeV. And the energy resolution at the beginning was a bit better, was 5%. In phase 3, it was 60% about, because I told you that we had 2000 photomultipliers, but part of them are dying. So now the present situation is a bit worsened by the loss of photomultipliers. But what is really important for Borexino and fundamental for the CNO measurement was the pulse shape discrimination. So we can select with high efficiency alpha and beta particles due basically to the time property of the scintillation process. And what in phase 1 we exploited the Gatti parameter that basically was a statistical subtraction. But then, thanks to the BIPO 214 coincidence that gives a lot of training samples for an alpha beta during the water extraction, we were able to tune a new discrimination event by event based on neural network, on multi-layer perceptron, and this is with high efficiency. And this was crucial, as we will see later, for the measurement of the CNO. I told you that one of the most important procedure was the water extraction. Basically, from mid to 2010 and mid 2011, we performed on the scintillator 6 cycles of water extraction. That is a process in which you pass the scintillator through the high purity water that is of course deionized and distilled, and this water is catching basically the ionic chemical contamination in the scintillator, and this was really crucial. As you can see from this table, if you compare before and after the water extraction, the bismuth that we will see, it's an important background for the CNO, was reduced by a factor 4 about. And the krypton was reduced. This is also important for the low energy spectroscopy, and for the beryllium-7 was reduced by a factor 6. Polonium also was reduced, and then we can also take advantage of the fact that the Borexino, the phase 3 is far away from the water extraction, so basically the polonium-210 is decayed. And also the concentration of the uranium and the thorium that we can determine assuming the secular equilibrium from the fast coincidence, from the BIPO coincidence, is extremely low, 3 orders of magnitude less than expected. I told you that the unit that we are using is count per day per 100 ton. Just for having a comparison, this kind of rate corresponds to 0.1 nanobecquerel per kilogram. Okay, so this is the typical contamination that it's extremely good, extremely radio pure. and you can compare with this number because you are used, for example, to dark matter experiment and double beta experiment. So you know how much is important having material lower than milli becquerel per kilogram, micro maybe becquerel per kilogram. And here we have 0.1 nanobecquerel per kilogram. Of course, not in the region of interest, for example, of the dark matter, but for higher energy. And this is the energy spectrum of the electrons scattered by the neutrinos, or in general, the beta-like event, because here we cannot distinguish between electron scattered by the neutrino and beta contamination, for example, and also other contamination. We applied some basic selection criteria. All events is the black curve if you do not apply anything. When you apply the muon veto and fast coincidence cut, you immediately reduce all high energy component. But what is really crucial is the fiducial volume cut, because I showed you that the inner vessel is 300 tons of materials, but only when we restrict the analysis volume to 7 tons, that is 7 tons out of 300 tons, so a small region inside in the innermost region of the inner vessel, we see the very famous Borexino spectrum, in which we see, as it is pointed by the red arrow, the beryllium-7 shoulder by eye. Then there is another improvement, and this was developed later during the phase 2. That is the threefold coincidence. What is the threefold coincidence? This additional selection criteria is used for vetoing the carbon-11. That is a cosmogenic produced by the spallation of the muons on the carbon-12. So it's a space-time veto that applies when a muon is crossing the detector and a neutron, spallation neutron, is produced. And it's able to remove this additional component that it's important not only for the beryllium-7, okay, because we can survive also without this cut, but it's crucial for the PEP neutrino and for CNO that have more energy and are falling in this region below the carbon-11. So in order to understand all the component, now here we have the map for reading all the ingredient of the spectrum. We see that the first excess of data is the carbon-14. That is our physical threshold, because I told you that carbon-14, it's really the concentration, it's recorded 10 to minus 18 as isotopic abundance in the scintillator, but it's still producing a lot of events, okay? So it's covering basically the low energy up to the end point that is about 150 kb. Then we have the first valley that is crucial for fixing a lot of spectra when we perform the spectral fit. Then we have this peak, and this is not beta event. This is the polonium alpha. You know that polonium alpha should have a bigger energy, but it's falling here because there is a factor 10 quenching. And so the reconstructing energy overlaps almost the beryllium-7. We were very lucky, because if the quenching were a bit different, the polonium could cover completely the beryllium-7 shoulder. Then in green here, we see the carbon-11, that the residual carbon-11, because the veto, the threefold coincidence veto doesn't have 100% efficiency, so we still have some residual. Then we have this peak here, that it's the external gamma contamination, that it's basically dominated by the thallium line. by the bismuth 214 and external potassium. But this, it's not a real concern because it can be disentangled in the analysis using the different radial distribution, because all the other contaminants are uniform in the volume. So they have a uniform distribution inside, while we know that the external background coming from the structure, coming from the nylon and the other structures surrounding the detector, has a radial dependency. Okay, so looking at the radial dependency and performing a multivariate fit, you can disentangle easily this component and increasing the sensitivity. And then we see these other three important ingredients that are this bismuth, CNO, and PEP. And you see that all the three doesn't have a clear feature, and they are almost degenerate. So when we started thinking about the sensitivity to the CNO, that is also published together with the Nature paper on the APJC journal, we understood that this intrinsic correlation among the three species reduces the sensitivity to the CNO, because basically the spectral fit is not able to disentangle them. They are strongly correlated. So it means that if you want to extract the CNO, you have to do something, you have to apply some independent constraint both on the bismuth and on the PEP. In order to understand this problem, I drew the schematic composite scale. You can understand the problem, because all the three are correlated. If you lock only one of the three, the other two are still anti-correlated. Okay, but we also understood during performing the sensitivity study that for sure, a strong constraint on the PP is required. But on the bismuth, we can accept, for the discovery of the CNO, we can accept only an upper limit, not necessarily a measurement. Because if we block the bismuth from the top, because we set an upper limit, the bismuth can go down, okay, but it cannot go up. It means that the CNO can only go up. So it means that if we stop the PEP, an upper limit of the bismuth is converted into a lower limit on the CNO. And it means that it's not reducing the discovery power. Okay. And in fact, in this publication, this problem is explained very well, and there is comparison between the neutrino discovery in both cases. In the case of the bismuth constraint and the case of the bismuth upper limit, we see that they are basically the same. And not only from this study was fundamental, because we understood that which level we should get for the bismuth, how strong should be this limit in order to get a reasonable significance for the CNO discovery. The first constraint, it's not a real concern, because in this case, it can help the solar physics. And what is called the luminosity constraint, that was first exploited by Pacol itself, and then it was updated. There are also two interesting recent publications from Francesco Vissani, for example, in which this is explained very well. The basic idea is that we can perform a constraint on the PP that it's quite solid and quite independent from the CNO flux, that is based on assumption of the luminosity, for example, of the sun that is measured with a high precision, on the PP-PEP ratio, because basically those two processes that are initiating the PP are related through the matrix element. So the ratio of the two, and including the condition inside the sun, the reaction, etc., are constrained with high precision. So basically, putting all these ingredients, you can get a strong constraint independent from the CNO on the PP. Okay. Basically, we could do also another thing. For example, we can measure the PP. We can use only the PP-PEP ratio. But PP measured by Borexino has a resolution, as accuracy of 10%. So it means that PP can have a constraint of about 10%. But this constraint from our sensitivity study, it's not really the best. Okay, a stronger constraint, it's required. So we decided to remove the PP from the analysis, not to use the low energy part, assuming the constraint from the solar model, and perform the CNO measurement. What about the other constraint? This is another long story because it was not that easy as for the PP. Bismuth can be constrained actually independently because we know that assuming the cellular equilibrium, it is related to the lead that is present out of equilibrium at the beginning inside the detector in phase 2 after the water extraction. So we have a very good alpha beta discrimination. So if we measure the polonium rate, we can infer the bismuth rate. But for this reason, you need to reach the cellular equilibrium. And this was clearly difficult at the beginning because we know that from the history of Borexino that there is a lot of out of equilibrium polonium in the detector. And we don't have the same evidence for the bismuth that is for the lead. Okay. There are different theories, but it looks like polonium is diffused out by material easily. And it was, if you compare the number, it's a real problem in the Borexino inside the detector. I told you that the water extraction reduced a lot the intrinsic contaminant, not completely. And one can think, okay, I just wait for the polonium to decay, and then I remove all the polonium out of equilibrium, and what is left is only polonium from the bismuth. This was not actually true because there is still a source term coming from the diffusion from the nylon vessel. So our understanding is that polonium is continuously diffused out by the nylon. Okay, so what is the idea? In the pure diffusive regime, the polonium should not be able to reach the analysis fiducial volume that is the 70 tons in the center, because it should decay before reaching the center, because it's 200. If you compare 200 of lifetime with the diffusion coefficient, in other words, the diffusion speed, that is extremely small. But how to set such a big detector in a pure diffusive regime? It was practically impossible because of the temperature variation, the seasonal variation of the temperature inside the experimental room in which there is Borexino. Just for people that are not used to visit our laboratory. The air that is present inside the laboratory underground comes from outside. It's passing on the top of the highway tunnel for about 4 or 5 kilometers. But the temperature of the rock is quite constant during the year because the mountain with its mass has a big heat capacitance. So basically, almost independently on the seasonal variation, the air in the lab comes with a almost fixed temperature, about 20 degrees, but still there is a small variation of 1-2 degrees. So damped, really well reduced as for the external seasonal variation. And this residual variation of the temperature in the hole was triggering the convective motion inside the detector. And we realized, realized that there was this convection just looking at the evolution, the spatial evolution of the polonium events. So what is the idea? It's to, we decided to start a thermal insulation program in order to prevent the formation of the convective motions and bring the detector in a pure diffusive regime in which we can perform the measurement of the bismuth or its upper limit. So we had two possible scenarios. The best scenario was that the diffusion regime is perfect and all the polonium cannot enter the fiducial volume. So we should see inside the fiducial volume a plateau. And from this plateau, we are sure that this is a real measurement of the bismuth. Otherwise, and this actually was the strategy that we adopted, you cannot reduce completely this kind of diffusion, but you have a very low region with a reduced activity in which you can apply the upper limit. This is the basic idea of the thermal insulation program that, as I told you, the basic idea started early in 2013 and 2014. First, we installed a lot of probes inside the detector and all around where it was possible in order to monitor with high precision the temperature in the detector. And what is the basic idea? It's to put an insulation all around the detector where possible in order to establish a strong vertical gradient that it's naturally possible in our laboratory because we have a floor that it's basically constant in time and it's about 6 Celsius degree that works as a big heat capacitance, and the warm air from the top. For example, this condition, it's not possible in Snow Plus because they don't have the detector in the open air in the same condition. So we covered our detector, we wrapped our detector with 2 layers of wool rock, and this started in mid-2015. We turned off the water recirculation system in the water tank in order to stop any possible movement of the water and so help the formation of the gradient. And then after covering the complete detector, we were realizing that the heat sink from the bottom was really strong and the detector was cooling down. So we installed an active control system on the top of the detector in order to keep constantly with a coil of warm water passing around, keeping the temperature of the top stable. And also with this condition, we realized that was not perfect because still we had some residual seasonal variation of fraction of degrees because the insulation layer was not completely capable of damping all the frequencies of the temperature variation. And the actual idea came late in 2019 when we installed an active control system of the inlet air of the whole experimental room, of the whole C. And this was done also thanks to the technician Graziano Panella from the laboratory who made the project and made the 2 feedback system to get this stabilization. And this was really impressive. And here you can see the picture of the Borexino before and after the thermal insulation. On the left, we have basically the metal of the sphere. And so everything can make some thermal bridge, and you immediately translate the variation of the experimental room inside and you create the convective motion. And this is after the insulation. So we covered basically all the detector, also the pipes, whatever, the floor of the top clean room, everything, whatever can be covered. Okay, and this is the insulation stopped finished in at the beginning of the 2016. And this is effect on the temperature. Before 214, we don't have all those sensors, so we cannot monitor the temperature. We cannot see how was really the situation before. We had also another set of probes that were originally installed inside, but we are not reporting them here. But before there was a strong oscillation, this change related to the change of the temperature in the experimental room, and after the insulation the situation changed drastically. We have a very precise stabilization with fraction of degrees, but what was really crucial was the final solution, that was the stabilization of the temperature from the inlet air from the pipe of the OLC. And this was really the best solution. But even in this condition, the effect on the events inside the detector were really surprising. And this is the situation. Where I put the blue arrow on the bottom, it's mid 2015 when we started insulating the detector. You see that before this date, before this period, we have those strong motion from the top on the bottom that has a cyclic seasonal variation related to the different warming up and cooling down of the temperature in the room. And when we installed the insulation, the situation changed completely. You see that it appears this very low energy. This is the polonium rate selected with the pulse shape discrimination in the region of interest. So you see how deep and how is the situation for the polonium inside the detector. Even if we didn't reach the perfect, as I told you, diffusion, the pure diffusive condition with a perfect plateau inside the fiducial volume. But what is important that we could observe in phase 3 of Borexino, a region with a very low content, very low activity of polonium that we called low polonium field, and it is reported with this name on the publication. And this region, it's not symmetric with respect to the equator, but it's located at around 80 centimeters above the equator. And we were surprising about this result. For this reason, we made a deep numerical fluid dynamic simulation. And surprisingly, also the thermodynamic simulation was confirming that the lowest region is not the center of the sphere, but it's shifted upward. Probably there is some physical explanation, but the fact that we had a strong confirmation from numerical simulation made the hypothesis that we were made strong the hypothesis that we were in the good direction. So the polonium that we measure in this low polonium field region is the sum of two contributions: the supported term that comes from the bismuth plus a contribution from the diffusion that comes from outside. And this is the sum of the two. Since this contribution is greater than 0, given the thermodynamic condition, we can state that the rate that we measure in the center of this polonium field is actually an upper limit for the polonium. It's cannot be used as a real measurement. Upper limit, as I told before, corresponds to a lower limit for the CNO, given the anticorrelation, that residual anticorrelation, once you fix with high precision the PP rate. The upper limit was determined with different techniques because, of course, you have to determine the rate in the minimum region. So for sure, you should be sure that your result is not biased. So we did many techniques. We exploited we were looking at the time evolution of this minimum region. We overlapped them using a blind alignment. We performed two-dimensional, three-dimensional fit of the low polonium field using a model, a paraboloidal model that is approximating the three-dimensional diffusive structure. And we also exploited model-independent modeling of the region using, for example, three-dimensional splines and so on. And also, we used some physical model, for example, steady solution of the Fick's diffusion equation with decay, with polonium decay. We cross-checked that all possible bias using toy Monte Carlo simulation, in which we simulate a diffusive-like structure and try to apply our method. We put everything inside our systematics, and from this study, using this low energy region, this low polonium field region in phase 2, we got as an upper limit for the Bismuth 210, 11.5 plus minus 1 CPD per 100 ton, including statistical and systematics error. But this is not the end of the story, because there is a missing systematics. We don't have a clear knowledge of the Bismuth, because Bismuth, we know that it's not diffusing as the polonium. We don't have this strong evidence. I mean, not really Bismuth, but the lead with the father is not diffusing out of the vessel. But anyway, we should consider any possible systematic due to the non-uniformity of the Bismuth. So the possibility that there is some gradient, some possible distortion with respect to the uniform distribution. Why? Because we basically are determining the polonium in a given region, small region, and then we are extending this measurement to the whole fiducial volume that it's larger. So in order to make this extension, you should be sure that the Bismuth is uniform. How it was done this study? We basically we selected an energy region in the Borexino spectrum far from the polonium, because this should be completely independent from the polonium. So it's a high energy window. It's basically a high energy in which the Bismuth is dominated over the other background and solar neutrinos. We know the percentage of the Bismuth spectrum in this window. So when we study the uniformity, we need to translate to convert into the total rate of the Bismuth. And we approached this problem with different techniques, but one that was promising, we basically splitted the problem in the radial and angular problems. The radial problems was studied using polynomial deformation of the radial distribution of the Bismuth event in this selected energy window, while the angular distribution was used an approach similar to the one used for the CMB studies. Actually, we were using the same software, that is the spherical harmonics decomposition. So basically, doing these two studies, we found that the Bismuth is practically uniform, and the systematics associated to the uniformity of the Bismuth, it's 0.8 CPD. And we summed up in quadrature the systematics to the error that we get from the minimum of the polonium. And we got the final constraint of the Bismuth 210 that is about 10%. Okay, now we have the two ingredient for the CNO analysis. This is the Borexino spectrum after the threefold coincidence. These are the three species of interest. Bismuth is blue, the red is the CNO, and the green is the PP neutrino, electrons scattered by the neutrino. I remind you that PP is a monochromatic line, but when you have interaction of a monochromatic neutrino inside the detector, you hit the electron, you have a Compton-like structure that is that gives this kind of continuous spectrum. PP is constrained to the luminosity constraint, 1.4%. Bismuth has an upper limit, so it's applied actually an asymmetric penalty using a half Gaussian. And we perform our standard fit, that is not actually this spectrum, but as I told before, it's a multivariate approach in which we fit simultaneously the threefold coincidence spectrum, the residual enhanced carbon-11 spectrum that comes from the threefold coincidence, and the radial distribution. The period used for this analysis goes basically from, it's the phase 3, goes from mid-2016. We decided to start in summer 2016 because the last operation, the insulation of the detector, stopped in January, and we basically removed 6 months for considering any possible transient in the stabilization of the detector. And the data set stops at the beginning of 2020. We are fitting the high energy region, basically. And we are applying the constraint for the PP with a symmetric penalty, while for the upper limit with a half Gaussian penalty. And we are using actually 2 methods. This is the multivariate fit. Then we also used another that is not actually an independent method, but it's like it's more a consistency check. We basically use the kind of counting analysis that it's inspired by our sensitivity paper, that is basically assuming given their uncertainty, all the contribution in a small region in which we have the maximum of the sensitivity to the CNO, and fix the other component according to their penalty. We know the total count of events in this window, then we subtract the contribution, and we propagate the systematic uncertainty and the strength of the penalty using a toy Monte Carlo. All the results are summarized in this final chi-square plot. Here you can see the chi-square, that is the dotted. Then is the continuous line is the final chi-square when we fold the chi-square with the systematic errors that comes from the toy Monte Carlo, toy Monte Carlo based on our Monte Carlo spectra. I will tell you later. And the red curve instead is the consistency check performed with the counting analysis. As we can see, the gray band. Why do we have this strange shape, this asymmetric shape? On the left, we are applying a symmetric penalty, so this bismuth gives this semi-half parabolic structure, while in the other part is given practically by the fit itself, because you have to consider the sum of all the species, so you cannot get CNO, you cannot get a high rate of CNO. When you increase the CNO, the chi-square increases. This is the 68% confidence interval, and that is the gray region, that is the Borexino measurement. And here we compare them with the 68% confidence region of the theoretical prediction for the low metallicity and high metallicity. Of course, given the errors, we cannot adding the CNO, we cannot give a strong claim, let's say, on the solution of the metallicity problem. For sure, for having a better having a better understanding of the metallicity problem, we need to increase the precision of the measurement. The systematics, as I told you, was was done by deforming the shapes of the Monte Carlo spectra in the range allowed by the Monte Carlo tuning, considering the distortion of the energy response, the resolution, and the light yield on the parameter that are important for the modeling of the Borexino response. And if you take the square root of the y-intercept, you get basically a 5.1 significance. But a better approach was done using an hypothesis test based on the profile likelihood, in which we simulated about 14 million pseudo experiments, and the conclusion of the significance using this frequentist approach gives that the hypothesis of absence of the CNO neutrino interaction is excluded at 5.0 sigma. This is actually, we performed also calculated also the model compatibility, but as you understood from the previous plot, from the gray band that is overlapping to the blue and the red, we are basically compatible with both high Z and low Z. But what is interesting, we using Borexino data only and including the experimental correlation, the theoretical correlation of all the fluxes measured by the Borexino, that is the PP, the PEP, and the boronate, we can disfavor LZ, so the low metallicity model, at 2.1 sigma. So this is basically the final result for the CNO neutrino in Borexino. So now we can complete and update our table. In red, we changed the previous upper limit to the present measurement, which has a large uncertainty, but 5 sigma discovery. So we conclude, okay, here I reported a quotation from Francesco Vissani, who has published an interesting post on his LinkedIn blog. Okay, for us it's really exciting, so I want to share this this feeling in this slide, but the real conclusion is that we performed the first evidence of the CNO neutrino in the sun. That means that this cycle actually exists, and so we match exactly the point in the PP CNO cycle competition inside the sign. We can easily believe that this mechanism is really important for the present understanding, for the present the present knowledge of the fundamental mechanisms in astrophysics. Thank you very much.
Thank you, Nicola. Thank you very much. This very interesting and very comprehensive and complete analysis of the Borexino history, and on this final result that is very, very important. So if there are questions, please raise the hand, and we can leave some time for discussion. Oh, Carlo, please, go ahead.
Ciao Nicola, and first congratulations for wonderful presentation and the wonderful results.
Thank you.
Yes, but I wonder, you know that the CNO cycle is regulated by the nitrogen 14p gamma reaction that has been measured by Luna, halving the neutrino flux due to the CNO cycle. I wonder how much it changed the scenario from the old flux of neutrinos that was appunto double with respect to the updated one by Luna in your analysis.
From our consideration, the relation should be almost 1-to-1, because we should expect like 10 CPD per 100 ton. a factor 2 more. So it means that this is more compatible for sure with the new measurement, no? Because if you go to this result, okay, you see there is a large uncertainty, but the central value it's 7.
Yes.
Of course, you should answer this question. If you trust the Luna measurement, okay, this is not actually the only ingredient in this game. But if you trust the Luna measurement, and this is correct, the result is quite compatible. At least it's not 10. I mean.
Okay, but using the old.
Using the old, I told you, it's a factor 2 more.
I'm just about that. Okay.
Yeah. It's almost 1-to-1.
Thank you.
Other question? There are some congratulations that arrived on the chat from Francesco Vissani, Laura Patrizia, Eugenio Coccia. So
thank you very much. I thank you all.
If there are no other questions, I have just a question from this plot, in the sense that what I see is that there are some, let me say that the data could improve adding to this, to the present analyzed data, what you collected during the last year, so in the 2020, let me say. What do you expect to improve the result, in the sense that probably, if I understand correctly from the plot that you show on the Bismuth to 10, going ahead time by time, the situation is improving, also from the point of view of the, let me say, of the capability to disentangle the contribution from the background respect to contribution to the signal. What do you expect to improve in the sensitivity plot, in this sensitivity plot, adding one more year respect to what you have analyzed in this paper?
From a statistical point of view, adding 1 year is not changing really much. I mean, it's reducing a bit the statistical error if the situation would not change. But what we expect, that's the reason why we want to study carefully the data that we are acquiring now, because we are entering this precise temperature stabilization, because we made this big change in the hardware, because we are stabilizing the whole room. It's that this region increases and becomes flat, as I also explained, because this is the real improvement. Because if it becomes flat, it's not only the error on the Bismuth, but it becomes a real measurement and not an upper limit. Okay, so it means that you can narrow the error, because you can put the asymmetric penalty, and you should be much more closer to a real measurement that tells something that it's really adding the significance to for distinguish between the HZ and low-Z model. There are also other analyses ongoing, because one idea, for example, is also exploiting the possibility of combining more data. For example, also the phase 2, removing, for example, the constraint on the Bismuth for phase 1, but keeping all the constraint for the PP. And from the preliminary sensitivity plot, it looks like also this method could be promising. So there are different approaches, but the real improvement should be a real change in the thermal stabilization that brings the detector in a pure diffusive regime, and we can claim that we have actually a real measurement of the Bismuth that goes in a real measurement with the symmetric error for the CNO.
Okay, that's very interesting. Other comment or question? No? So I would like to thank Nicola again, and I would like to congratulate one more with the Borexino collaboration. And I think that it's a very successful and very impressive result that was obtained in the last, or we are almost close to the 15 years, so there are a lot of time that Borexino is on the top of the research activity in the world. Thank you. Thank you also.
Thank you. Thank you.
Can I ask one question in the last minute?
Yeah, if you want.
So, I mean, this is a fantastic result, and I would say that all results from Borexino are really exceptional. Congratulations. I'm very happy about the whole collaboration. Now, what do you plan to do next? What are the plans for the future?
Maybe I can let the director answer this question.
That's a very difficult question.
Yeah, because it's a delegate question, so it's better if the director.
In a sense that Borexino is arrived practically at the end of the story, as I can say. We have a plan for the final. Let me say the final decision for the detector will be that we will go to the, let me say, to the decommissioning phase starting next year. So we are working in this direction. We will the detector will remain active for all the time, but probably during the, let me say, end of winter, beginning of spring next year, we will go to switch off the detector and to start the decommissioning phase of the Borexino experiment. There are some constraints that I don't want to explain now, but we are moving in this direction, let me say, in a few months from now.
Okay, thank you. I can also add that as we are trying to follow the experiment, try to keep as much data as possible in order to see if we can gain something for the last months of thermal stabilization, and as I explained before. So we will try to keep as much as data as we can, and until the decommissioning phase.
Okay, thank you. But Borexino did. I mean, what expected, and actually what was not expected.
Exactly.
Yeah,
exactly.
So it's fantastic, really. Whatever. I mean, whenever it's decided to be dismantled, I mean, it is a fantastic experiment, and it was copied by many other experiments. The detector. Thank you.
Thank you to you.
You're welcome. Thank you to you.
You're welcome, Javier. Other comments? So if there are no other comments, we can close here. And thank you again to all of you. And I hope to see you again for another important result from the lab, from the Borexino, for another experiment in the near future. Okay. Thank you to everyone.
Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.
Bye. Bye.